we're going to talk about velocity modeling and what we have in the 10EP2 release. My name is Larry Fink. I'm the product manager for velocity modeling, and I'm pretty excited to showcase what we have new in the velocity solution for the 10EP.2 release. But before I get to these great new features, I want to just talk about the value proposition of why the velocity model is so important in the G&G workflow. Just think about this. If we've got a discovery well here on the left and an offset well on the right, without any other information, we really don't know what's going on in between the wells. So we might as well be like a three blind mice trying to figure out what's going on between there, again, without additional information. We do get additional information to help us in the interpretation of what's going on between the wells. And in this case, 3D seismic, a lot of people will tell us that, oh, that gives us almost like a well every 25 meters if it's good seismic. And so we have this great seismic image of what's happening between our wells. But that's not exactly the rose garden that we thought we were getting, because the problem with this seismic is that these are just images, and that, like this fault here, it could be a quarter mile laterally shifted when we put it to reality if our horizontal velocities are incorrect. The top of this structure could be hundreds of meters off if our velocity is too fast or too slow. And the thickness of this structure could be hundreds of meters off if our velocity is too fast or too slow. But if we can get the velocities correct, then this image, it does become sort of reality. And if we look at this, the velocity model can turn the seismic into this magic that does create an accurate sort of structural representation between the wells. And the reason that's important is because the main uncertainty components for most of the reservoir economics when we're drilling, when we're siting on the fields, is the reserves, okay? And if we do a standard risk tornado chart, typically the reserves shows up on the top. That's the most risky thing to make our prospects economics, is the reserves. Now, the last year or so, of course, the most risk has been the price, but these toggle back and forth between what's the biggest risk factor. One of the giant risks for the reserves is the structure, and if the velocity model, it can move that structure up and down, which is going to change the oil-water contact, or if you're in a petroleum systems model, that's going to change, you know, where the oil generation zone was. So if there's oil even there, you're drilling a well, the velocity model can move the faults laterally, so it's going to change your well plans and moves the structures laterally too to change the well plan. And again, for the volumetrics, it changes the thickness of the gross rock volume to, again, change the reserves, change the economics. It makes a big, big deal on our prospects. To drive this home even more, I just have a few images to show, okay, what's the seismic image versus what's reality? So if you think of the reservoir sort of volume as the depth image on the left, and the seismic reservoir image is what's on the right. So if we're in a fast velocity zone like a salt or carbonate, our seismic image gets squished. It's too short and stubby compared to what's reality. If we're in a slow velocity region, say like a overpressured shale, that seismic image gets vertically stretched and gets way too big. So we used to get away with this. We're 50% right, that's okay, just average estimate of velocity. But as we become getting some better velocity models, if we have stratified Earth where the velocity is changing just vertically, you know, again, the seismic image gets distorted and stretched and compressed, and we got to take that back to our real sort of reservoir image on the left on this image here. Now, when the velocity is in like a hard rock zone where you have structure, the seismic image gets even more distorted and starts wiggling around more like a funhouse mirror. And at that point, you need even a better, more accurate velocity model, which we sort of came up with in the 90s with Depth Team Express. And then going forward, when we're getting these bigger, more anisotropically complex velocity models, The seismic image gets even more distorted if the velocities are a function of the propagation through the Earth. So if the vertical velocity is different than the horizontal velocity is different than north velocity versus south velocity or east-west velocities. Again, to get the reserves accurate, we'll need the velocity model to be able to distort this funhouse mirror effect of the Earth. And then last slide before we get into all the great new features that we've added for this solution is just the general industry problems are, a lot of the velocity models can be non-unique, and people oversimplify the velocity model, make it just an average or just something that's very, very simple. And that gives us a distorted picture of reality. And then nowadays we're getting much larger, more complex surveys. We're trying to be more accurate with the velocity model. And of course we need it much, much faster. And so we're striving with the velocity solutions to be able to handle all these big complexities in the velocity model. So we're going to not be just a simple homogeneous velocity model. We're not going to just be a simple isotropic velocity model. And we're going beyond the isotropic laterally changing velocity model to velocities that are more representative of what's going on in the Earth, meaning that the velocity, if you're going parallel to the bed, is typically much faster than if you're going vertical to the bed. So it's not horizontal to sea level. The velocities are really a function of how you're propagating with respect to the orientation of the geologic layer boundaries. And there's a lot of that goes into this, and that's really for a different talk. So I'll just say that if we need to get horizontal and vertical velocities correct, and azimuthal and anisotropic velocities correct in order to get the seismic images correct. We're very excited about these features, and I'll go through and show some of these guys live. We can. And the first thing I want to talk about is we've got the DepTeam Express plugin now integrated directly part of the 10EP.2 release. The DepTeam Express velocity modeling package, it's been an industry standard for many, many years, and it's really great for geoscientists who are performing simple domain conversion for well planning, for volumetric analysis, typically in sort of a non-salt, non-overthrust, sort of non-complex region. And DTE, DepTeam Express, has a lot of extensive QC tools, analytic velocity modeling tools. It even has some uncertainty analysis tools. And there's also a lot of features in the DepTeam Express plugin that don't exist in the DecisionSpace velocity modeling package. So these packages work hand in hand together. You see you launch them right next to each other, velocity modeling versus velocity modeling DepTeam Express. They're the same license. They create the models that are used identically for like domain conversion or inversion or anything you use a velocity model for. So you have the choice of sort of two different velocity modeling packages to use here. So let's take a look at what the DepTeam Express looks like within the 10EP environment. Simply, you go to the tools, you launch the DepTeam Express module, and it pops up into what you're used to seeing, the model manager. And the DepTeam Express model manager, if you're an Express user, you know exactly how to use this now. The big deal is the model manager for DepTeam Express is directly embedded into DecisionSpace. So when you build the model in Express, it immediately will show up in the DecisionSpace views, in whichever you have turned on, the cube view, map views, section views, and it has the direct communication with the views. So if I'm in the DepTeam Express dialogues and I say to display my log curves or my time depth functions, it will display those directly inside of DecisionSpace. And so if we play with the display parameters in DecisionSpace, we can toggle things on and off from the DepTeam Express views. We can update the model, and it immediately shows up in my QC views in the DecisionSpace viewers. So for example, if I turn off this pick or a bad pick, watch what happens to the well right here. The model gets immediately updated as we update it from Express. The views are tied in and updated in DecisionSpace. Now, of course, we can do the same thing for changing surfaces, changing volumes. We can display the models in the cube view. They display sort of like seismic volumes in the cube view. So a really good QC. This used to be QC'd in OpenVision, but now we have a lot more powerful QC within the DecisionSpace viewers. And same thing with the map view. These models show up in the map view automatically. And then, of course, you can save the model as a standard velocity model, again, to use for domain conversion, inversion, whatever you need velocities for. They're saved in a standard format. And again, the models are all compatible with previous versions of DepthTeam Express. So we're very excited that we have that in there. Now, the next thing that we added that we're excited about is the workflow for depth stretching. Now, if you're not familiar with what depth stretching is, we're taking seismic depth migrated volumes that has the vertical axis labeled as depth, but that's really what we're calling seismic depth, because we've used a velocity function to get it to depth, but the problem is that doesn't actually tie our wells. That we know this depth velocity model doesn't tie the wells, so we've created this depth stretching tool to convert seismic depth to well depth, and that will kind of stretch and compress it down to this workflow. It's much more efficient than what we had to do before, so we're going to save disk space and time in order to just directly convert our seismic to get it to a depth tide. And you would use this, geoscientists would use this whenever they're drilling a new well, say like in a subsalt zone, or if you get a new depth migrated seismic volume. And this is really great and really powerful for geoscientists that they're drilling subsalt and to predict the reservoir tops, to predict, importantly, where the pressure tops are. It's a very, very safety tool, because you really need to know when you're going to hit pressure when you're drilling these high pressure, high temperature wells. And of course, you really need to know when you're going to cross a fault or something, so it's going to get you better, more accurate fault placement and structure placements in the subsalt by applying this depth stretching workflow. So within DecisionSpace, how we're doing this is it's just a mouse button 3-click on a volume, and we select the depth algorithm, and we'll give it some parameters there, and I'll show you what we can give it, and we can produce a QC volume too, so you're not doing stretching blind. You get to actually see the depth model that's used. This is just showing a model stretched versus not stretched to tie the wells, and I'll show another picture of this in just a minute too. But so it's just similar to a time depth stretching, but just a lot more efficient in the depth domain. And then here's a picture of the QC volume that is applied. So the QC volume is basically a whole bunch of stretch values. So do I stretch a little bit? Do I stretch positive? Do I stretch negative in order to get it to tie? And so this shows you what the stretches look like between the wells. So let's see how we actually run this. And the big thing that we do first when we run it is we actually will generate depth stretch time depth curves. They're not really time depth curves, they're what we call depth curves. So if you button 3-click on a well and say well tie, well, it's a completely different workflow if you're tying depth data versus tying time data. So in the seismic analysis tool, you select to do a depth well tie. And then what that's going to give you is depth curves that tell you how to properly tie the seismic data to the well data in depth rather than in time. So once we have done the depth well ties, we can use that well tied information to generate a full volumetric well tie velocity model that's going to stretch our data from seismic depth to well depth. So here we can select whatever depth curves that we want. We can select whatever wells that we want, and we can choose to create our QC volume. And then it runs, it's threaded, it runs very fast, but it won't tie up your system while it's running, so it makes your workflow much more efficient. And then it immediately loads it into your view, so you can just toggle back and forth between your depth views, and you can look at the QC of the structure. And then look, watch this well right here. So that's tied, not tied. tide, not tide. So we do nice QC of our depth stretching algorithm. So we can QC the model that was made, and we can QC the seismic back and forth interactively. Very powerful. We're going to be able to predict the pressure tops and fault locations, certainly in the high pressure, high density areas, much better with this workflow. Another great feature, we have a lot of great features to talk about, is our layer-based velocity analysis. And this is really great for, say, the geoscientists that are predicting, again, fault locations, reservoir volumetrics, but in just general hard rock regions where velocities typically are a function of the geologic formation that you're in. So you think of Europe, offshore Norway and stuff. Now, our issue with velocity modeling is we have sort of an oversampled solution here. So if we're doing a layer-based analysis in a chalk zone, in this case, well, I have 5 different measurements of velocity versus depth within the chalk zone, and you can see that these velocities, whether they come from sonic logs or they come from check shots or seismic velocities, they're all a little bit different. So it gets confusing as to which velocity should we use. And you can think about this as like, if you have a watch, you know exactly what time it is. But if you have 5 watches, you're really not sure what time it is, because those watches aren't necessarily synchronized and they're all giving you a little bit different time. Well, here we have 5 watches that are 5 velocity measurements from seismic and check shots and things that don't exactly tie. So we have to have a method to analyze, okay, are these good velocity measurements? Do we have any anomalies? Is there interpretation that's bad? What's going on here? So we want to get the best due diligence in the velocity model. We want to have the best data coming in. So that's what this zone analysis tool is for, is to be able to calibrate these different types of velocities to see how they work together. And the first thing, QCing and analyzing these multiple types of velocities, is just being able to look at them. It used to be when, like, the time depth curves or the check shots came in, we just looked at them in spreadsheets views, or a view like this where we could overlay a whole bunch of time depth functions or check shots with each other. But now we've added a tool to just be able to look at these as standard log curves like our geologist friends are used to doing. And it's really powerful to be able to take the check shot and display it as a velocity log versus our seismic velocity model, or just versus the seismic itself. We can QC, okay, does this check shot look reasonable? Does the velocity model interpolation of the check shots look reasonable? Very powerful, giving us a more accurate velocity model for more accurate volumetrics and such. So I'll show you just quickly how that is done. You simply mouse button 3 click on the well list, and you go into the well details tool, which you could do a whole bunch in here. But the main thing I want to show is we can go directly into the time depth curve editor, and from that editor, instead of editing it, we can just save time depth curve as a velocity log. Now, if I want to save an entire well list all at once, I can do that from velocity modeling. I can select all my wells or just certain wells, and I click the Save as Log Curve button, and it's going to save all of those check shots as log curves that can be displayed with the power of the log display that we have in DecisionSpace there. Now, we worked some with the view for displaying the log curve. So again, if you can just mouse button 3 click on the log curve, you can set the display parameters. Very easy, very much like you would just do stuff in PowerPoint. So you don't have to be a well template expert to display your velocity log curves. You just button 3 click on it, go into the display parameters, select the color fill. In this case, we always want to do the color fill, the same color fill as the velocity model itself, so we can compare those guys together, as I showed in sort of the previous pics. But here you see how beautiful the check shots look, or the time depth curves look, with respect to the seismic data. And I could put the the velocity model over here too, but in this case I haven't actually built the velocity model yet, but that'll be a really good QC for that. And you could do the same thing in the cube view. You can display the velocity log curves in the cube view. Simple mouse button 3 operations, good due diligence for checking that part of the velocity model. To do more detailed analysis, we want to check not just the check shot velocities, we want to check, do our picks look correct? Does our time interpretation look correct versus the depth pick on the well log itself? Is our interpretation right? So this is just a picture showing what our spreadsheet columns are going to look like. So if I say this is what the depth top looks like, well, this is the time top. Do those actually tie? So we want to do a lot of sort of zone manager type analysis of the velocity regions. So in this case, maybe if we're looking at the chalk zone or reservoir zone or a shale zone, we can dynamically define these zones and go through a spreadsheet analysis and look for anomalies. And we can think, the velocities in general should stay consistent within the zone. If not, is it a problem because the well is highly deviating, we're getting a strange measurement? Can we explain it through phase changes, or do we just need to throw out the bad data? So it's a great QC tool, whether you're QCing in the spreadsheet view or in a cross-plot view. It's a great QC of layer-based QCing of the well velocity data versus the sort of the more seismic velocity data. Let's just take a look at how that is done. Again, just in velocity modeling itself, you can go to the well surface picks tab, and we have the pick details option, and you can sort any of the columns. So we can look at the change in velocity versus the check shot changes in velocity. We can see if there's interval velocities are being consistent. If not, why not? Can I explain it? Why is this well different? I can look at any different zone just by clicking on what we want to use for the base. And so here we can do an interval velocity analysis on our chalk zone. We can plot the time versus depth from that zone and see, okay, is there a linear relationship between the velocities? And we can calculate a linear regression through there and say, yeah, my velocity from all my wells within this zone, look to be following a nice trend. So maybe I'll believe that these are actually realistic values and can trust these. Okay, whereas the other zone might have had that anomalous interval velocity. We want to maybe go back and look, did that get faulted out? Was that did we jump a leg on the interpretation or something? So like anything in geophysical analysis, it's garbage in and garbage out. You want to only be working with good data and data that you can defend. A lot of velocity modeling is QCing the data and making sure you're using the proper data. The next big feature, and this is one that I think a lot of people are most excited about, is that we're adding in this giant regional velocity modeling workflow, and the regional workflow is going to be based on geostatistics and giant regional 2D seismic data. And that was something we didn't handle very well before, but now we are handling it in this new release, and we've got a big 14-step workflow in order to handle these giant models. And for the 10EP2 release, we're doing a little more than half of the workflow, but we still can make valid, really good geostatistical models with just the first half of the workflow and that we're doing in 10EP2. And so think about 1 million square kilometer velocity models at good performance using giant seismic input, wells that are just very farly spaced apart, but we're going to integrate in the power of the Earth modeling, integrate in the power of the 2D mapping into the solution. So we're combining to our one sort of global Earth model, one representation of the subsurface, and we're getting all of our modules together with this workflow for velocity modeling, Earth modeling, 2D mapping, geology. Everything is coming together quite nicely here. So again, think about a million square miles, and these X's represent where the wells are, and you can see the wells are tens, hundreds of miles away from where our seismic data is. We're going to use the power of geostatistics, variogram analysis and stuff to properly calibrate and tie the seismic interpretation, time interpretation, and the seismic velocities with the velocity information and the pick information from the wells. And it's a powerful tool for regional modeling. And again, this is typically for, say, like a basin modeler or a regional geoscientist, be in charge of mapping, say, the play fairways or the golden temperature zone of hydrocarbon generation in the basin. These tools, they will also scale to just prospect level velocity modeling too, if you choose to do so. The key thing that we had to add in order to implement this workflow is to be able to input grids as structural control surfaces. Before, we would only input seismic horizons, which typically required 3D data. Now we do not really require much 3D. We can build much better models just using the surface grids as input. So that allows us to do these regional 2D and multiple 3D survey velocity models. And we've tied together these tools. We have options within velocity modeling. We can go directly into grid and contouring if we want to tie our time interpretation based on our check shot analysis that I showed earlier. We want to calibrate the time structural interpretation, but we want to intelligently calibrate that using the geostatistical kriging and variogram analysis. So we get a great time surface from very, very sparse data, the best scientifically managed time surface that we can come up with. And then we do the same thing with the velocities. We'll extract the velocities from hundreds of 2D seismic lines and send that velocity extraction to the Earth modeling sort of geostatistical analysis tools to give us the best velocity interpolation in the sparse area where we don't have any other velocity information. So again, this is the big tie together, is we get to use the power of Earth modeling and 2D mapping with the velocity data, so we can, with the time velocity data for our time structural surfaces and with our 2D seismic interval velocities, we can define the variogram and we can geostatistically interpolate the velocity models quite well. So let's take a look at how it's actually run. So I got my giant 2D prospects here, and I can do my check shot analysis. I showed that before. And then we go into the 2D velocity. So again, when I select, I can select multiple 2D line lists. So I can select hundreds or thousands of 2D lines of seismic velocities to analyze. And then I go ahead and I select, okay, what layer do I want to analyze? Do I want to analyze, typically you'll go from top down, but I could analyze, say, like my chalk zone in this particular example, or I can analyze my shale zone, and I want to get the velocities from the seismic. So I'm going to take my seismic stacking velocities, convert them to interval velocities, and I'm going to create a point set of those velocities at whatever resolution that I choose. Now, there's some QC. Okay, did this velocity conversion look correct? Were my top and bases too high or too low? Once I've done that, I get to see a point set of my regional 2D velocities for the particular zone. So in this case, in the chalk zone, these are my 2D interval velocities for my chalk zone. Again, it's very sparse, over 1 million square kilometers. So I can take my sparse analyzed seismic velocity information and take it into the 2D mapping. Now, again, I can do it for my time surfaces, or I can do it for the velocities themselves. I'm going to actually do it for both here. I'll show for the velocities. I can do some geostatistical analysis, throw out some outliers. I can use all of these algorithms. If you look at all the algorithms that we can do for gridding and interpolating between our sparse data, the big thing we've added is the anisotropic kriging, and we can do the full Earth modeling variogram analysis of our data to get the parameterization just right, the way the geostatistical experts would like to parameterize the data. So again, I'm going to use azimuthal interpretation, so I want to define my variogram along a certain azimuth, and I want to define the minimum and maximum axes for the variogram. I get to do this as if I'm an expert geostatistician, and to get what we think is the most geologically intelligent interpolation of the velocities. So here I see the major and minor axes. I hit the run button, and I have geostatistically interpolated time surfaces or velocity surfaces that I can use for my velocity modeling. And we've given the users lots of control of how the velocities and structures are interpolated by enabling this workflow and taking advantage of Earth modeling and our 2D mapping solution. The final thing that we're also, of course, excited about is just some usability updates. And I've already shown some of the updates with like the time depth curves, how it allows you some good due diligence of the time depth data coming in. We can save well lists now just to calibrate with the asset team. I'll show you two other really nice options that we've added, and that's just displaying the velocities along the seismic surveys. So before, this is what it looked like before. When we had a velocity probe, it was north-south. This gray rectangle is the actual seismic survey, and the blue is the water velocity, but that's the velocity model that doesn't tie with this survey. And that same thing if we look at it in a map view, you can see that the display of the velocity model, it extends out beyond the survey. And it really distracted people because they said, well, I don't have any data out there. Why do you put velocity stuff out there? And our thought was, oh, well, what if we wanted to look at something out there? We want to domain convert out there. But it became too much of a distraction. So what we've added is by default now, we just say, okay, we're only going to display the velocity model within the survey, because that's really what it is. The other thing is just extrapolation. It doesn't change anything, but we're just going to get rid of the distraction, the external distraction. So again, by default, you'll see the velocity model snapping directly inside the survey. Okay, so that's great for the map view, but for the probe view or the cube view, what we added is just the option we say load directly to cube. So instead of a new probe, we're going to just load the data to the cube. And when we do that, you can define to load it as a time volume, depth volume. You can load any of the attributes. So if you had your horizontal velocities or your anisotropic parameters, you could load those in and view those in the cube view or actually in any of the views just by this simple mouse button 3 operation. And when that happens, it's loaded really just as a seismic volume. So you have all the power of seismic cube probe displays. So we can see now we are exactly inside the survey, and you get the power that comes with the seismic display. So you can lock the probes, you can lock the orientation. It's really good QCing two different velocity models together in this method. You can overlay them. And of course, you can use the power of the display properties for blending, with the seismic if you want to in the dynamic world. You could also do combo mambos and volume rendering, RGB blending with the velocities now with this workflow. So really good QC for people wanting to check their velocity models, justify their rock volume estimates, basic due diligence. Is my velocities and seismic scientifically valid? Are we in the right place? That is big parts of the new great features. I just want to close with saying that truly the velocity model affects all of GNG workflows. And the more accurate you can get this velocity model, the better your well planning, poor volumetrics, poor pressure prediction, everything is better if we can bring all the data in this single subsurface model representation of the Earth. Thank you.